Hi everyone, and welcome back. Believe it or not, we're now in week 13 of this course, and the last couple of weeks we've been focused on hypothesis testing, where we compare one mean to a value, we compare two means to each other, and in this week we're going to be extending that a little further to talk about comparing three or more means. So you have three samples that each have a mean, and we're going to be doing a hypothesis test based on that. But before I do that, I just want to introduce my new friend who's been sitting on my lap this whole time. All right, so also before I do that, I want to talk a little bit about the schedule for the next couple of weeks. So we really are in the home stretch of this class now, so I'm just going to lay out what's coming for the next couple of weeks, what's going to be due, and so on. So this week, the week of April 12th, we are, as I just said, going to be doing this topic of comparing three or more means. We have a problem set due this week as usual, so that'll be problem set 11. Next week will be week 14. We're going to be doing two different kinds of hypothesis tests in that week called chi-square and correlations, which is partly hypothesis test, partly some other stuff you'll see. There will also be a problem set due next week as usual. Next week, I'm also going to be assigning what I call in the syllabus the Applied Data Analysis Project. As I've said before, it's less big project, more just an assignment in a different format that'll be applying a lot of what we've been talking about over the last couple of weeks. But I'm going to get into the details of that next week, because at that point we will have learned everything that you need to know in order to do that project. The final lecture of the course, so we've got this week, next week, and then one more week of lectures, and then we're all done with lectures. The final week of the course is my favorite lecture, which I call Who Cares About Statistics, because the answer is me, and then hopefully some of you guys by the end of it. During this week, there will also be problem set 13 due. As a quick reminder, only your top 12 problem set grades count in this class, so if you're happy with your grades, by this point you don't have to do it. Otherwise, do problem set 13, and then I will drop your lowest score. And then finally, that'll be our last week of class, week 15. We'll be into finals week. There is no final for this course, so you don't have to sit for a test or anything like that. But during finals week, the short report from that Applied Data Analysis Project will be due. And so that'll be due on May 12th. So you'll have a good amount of time to work on that after it's assigned next week. And then just as a reminder, your lowest problem set grade will be dropped, so just keep that in mind as you look over your grades and as you think about these next couple of weeks. As usual, if you have any questions about the schedule, the material, anything else, feel free to reach out. That is what they pay me for, so you're never bothering me. Just shoot me an email and I will get back to you pretty quickly. All right, so with that, I'm now going to get into the material for this week. And so what we're going to be doing here is comparing three or more means to each other using samples. So as you'll see, this is really going to follow from what we've been doing in the last couple of classes, where we looked at one mean, then we looked at two means, and now we're looking at three means. And we'll be able to answer questions like these. So do people in urban, rural, and suburban areas have similar perceptions of the fairness of the police? So you have three different groups, urban, rural, and suburban, and you'd be comparing the mean levels of perceived police fairness among those groups. Are sentences assigned equally for Black, white, and Latino people in the courts? So there again, you have three groups, and you'd be comparing means across the groups. Do drug offenders, violent offenders, or sex offenders have the same recidivism rates? So there you'd be comparing recidivism rates across offenders grouped in three ways. So you might be wondering, or maybe you're not wondering, but you might be wondering, why don't we just use a bunch of t-tests to compare across these three groups? So why don't we compare urban and rural and suburban, and urban and suburban, and just do a t-test for each one? The problem with this is that when using t-tests, you can only compare two categories at a time. So you can only compare one thing to another thing, and then one thing to another thing, and one thing to another thing. Because of that, you have to do a whole lot of tests. And if you do multiple tests in a row to get at the same question, you have more of a chance for a false positive. So it's always possible when you do any sort of hypothesis test that you're going to get an unlikely sample just by chance. And the more hypothesis tests you do, the more likely it is that you're going to have something unlikely just by chance. And so we're going to really come back to this idea in the final week of false positives and what that means in practice for interpreting hypothesis tests and significant results that you see in the world. For now, you can just take my word for it that the problem with using t-tests is that the more hypothesis tests you have, the more likely it is that you're going to reject the null hypothesis accidentally. So instead, we use a test that allows us to compare multiple means at a time. So typically used for 3 or more means, because if you only have 2, you can use a t-test. And this test that we're going to meet today is called analysis of variance, or Anova, as it's generally referred to. So when doing an Anova test, like in any other hypothesis testing, we're going to have null and alternative hypotheses that we're going to be testing. Your null hypothesis in an analysis of variance test is that all the populations you're interested in have the same mean. So we're comparing across multiple groups. So if we're saying rural, urban, and suburban, our hypothesis is that they all have the exact same mean on whatever it is we're measuring. So you could write this as the mean for one population is the same as the mean for another population, which is the same as the mean for another population, which is the same as the mean for another population for as many populations as you have. So in all of those examples that I gave you on the last slide, we were looking at 3 groups, but you could run one of these tests for really any number of groups you have. So if you're comparing 4 populations or 5 populations, or even more, technically you can do one of these. The alternative hypothesis is that all populations do not have the same mean. So as usual, our alternative hypothesis is just the inverse of our null hypothesis. It's once you rule out the null hypothesis, what's left? So if we rule out the idea that all populations have the same mean, we're left with the idea that all populations do not have the same mean. One technical point, though, that always trips people up, so I like to highlight it on this slide here, you wouldn't write that like this. So this statement here says that the mean for one population is not equal to the mean for another population, which is not equal to the mean for another population, which is not equal to the mean for another population, where etc. there just means you could kind of do that forever, for as many populations as you have. The reason we don't write it as this, though, is that the only thing we're able to rule out is that they all have the exact same mean. But we don't actually know which population is different from the others, or if they're all different from each other. So if you rule out that statement on the top, it's also possible that this is true, that your first and second populations actually do have the same mean, and it's just your third and next ones that don't. Or it could be that your second and third population has the same mean, and then these other 2 don't. Or really lots and lots of different possibilities, where in all of these cases, it's true that all populations do not have the same mean. But with this test, we're not actually saying which population has a different mean than the others. It could be that they're all different. It could be that only one of the populations is different. You could be running one of these tests for 10 different populations and comparing 10 different means, and if only one of those means is different and all 9 others are the same, you would still reject the null hypothesis that all populations have the same mean. So to sum up here, when writing null and alternative hypotheses, I recommend just doing it in words. You can skip the mu1, mu2, mu3, and so on altogether, because your null hypothesis is really just that all of your populations of interest have the same mean, and your alternative hypothesis is that all your populations do not have the same mean. And we're not going to get anything else out of this test in terms of which populations do or do not have the same means. All right, so let's talk a little bit about what this test is and how it works. So this is going to be the first hypothesis test we're going to talk about that isn't using a t-distribution. And that's not some version of a t-test. So I'll talk about the distribution we're looking at in a second, but first I'll just talk about what the test does. So the analysis of variance test compares variation between groups to variation within groups. So between groups refers to differences between samples drawn from different populations. So if you took a sample of urban people, a sample of rural people, and a sample of suburban people, and compared the mean level of support or perceptions of fairness that each one had of the police, your variation between groups would be a measure of how different those sample means are from each other. So maybe people in your rural areas see the police as really fair, people in urban areas tend to see them as less fair, and people in suburban areas are somewhere in the middle. So your variation between groups would be just describing how big those differences are. So how different your sample means are from each other. Variation within groups, on the other hand, refers to within each sample that you take, how different are the observations from each other. And so here you want to think more about standard deviation. So for example, if you've got your rural, urban, and suburban samples, maybe in your rural sample, everybody kind of answers the same way, but maybe in your urban sample, you have some people who perceive the police as really fair and some people who perceive the police as really unfair, and there's just more variation, even though overall it has a different mean. And as usual, I'm talking through this here, but then I'm going to go through some examples, and I'm going to sketch out what's happening with some diagrams and so on once we go over to the document camera. But the key thing about the analysis of variance is that you're comparing variation between groups, so variation in sample means across different samples, to variation within groups, so the differences within each sample that you take, and you're going to be using those two things to draw a conclusion about how likely it is that all of the populations you're sampling from have the same mean. And to measure variation between groups and variation within groups, we're going to be looking at two measures that we refer to as mean square measures. And I'm not going to go through where they come from or how they get that name. We're just going to go right to interpreting what they are and then taking a look at how they are used to calculate a test statistic for this hypothesis test. But there's two types of mean square variation. One we refer to as mean square between groups. And the between groups mean square is a measure of how similar or different the sample means are to each other. So again, if you're sampling from three populations, you're going to have three different sample means, and we're going to see how similar or different are those sample means. You've got your within groups. Your mean square within groups is going to be a measure that summarizes how similar the different members of each sample are to each other. So across all three groups you're looking at are, members of each group really similar to each other, or do you have more variation within each of your samples? And these two measures, so your between groups mean square and your within groups mean square, are used to calculate a test statistic referred to as an F statistic. So an F statistic is similar to a z-score, it's similar to a t statistic in that it is a statistic that can be plotted on a standardized sampling distribution, and then you can use it to calculate a p-value to tell you how likely or unlikely your sample is. The F statistic is larger when you have high between group variation, meaning it's larger when you have big differences between your sample means. It's also larger when there's low within group variation. So it's also larger when members of each sample tend to be really similar to each other. So you'd have a high F statistic if your rural, urban, and suburban sample means were really far apart. You'd also have a large F statistic if members of your rural sample were really similar to each other, members of your suburban sample were really similar to each other, and members of your urban sample were really similar to each other. So here's my talking slide. Now I'm going to head over to the document camera. I'm going to sketch out some of these things. I'm going to start going through some examples, and we're going to come back here, talk a little bit more about the hypothesis test itself, and then I'll go through an example of that as well.